Like a lot of people, my first gaming experience was Doom. It made a big impression on me, and when I learned how to program, I always wanted to bring 3D worlds to life using my mind. Well, it turns out it took nothing short of wizardry to get the first 3D games playable. Traditional graphics programming algorithms were hampered by hardware, and that's exactly what I want to investigate today. What if the hardware of the 1990s wasn't cringe? Imagine a system which can not only handle floating point calculations, but can also use SIMD to handle multiple calculations at the same time. What kinds of algorithms could have been used if computers were better at handling math? Let's take a look. Hop in the time machine with me. Alright, so I guess before I really get into this, I'll briefly talk about the system that I'm working with. I have got an array, an array of pixels, heaps of pixels, and they're all vec3s, so they have, red, green, blue, alpha components. There's a whole bunch of them. And then the goal is to write that onto the screen, onto a screen image. And basically what I've got is on the CPU side, I write to this array, and then I use a Vulkan compute shader, which is operating 1 pixel at a time. It takes the appropriate pixel and it reads it in there. Because I'm doing a raycasting algorithm, I will mostly be drawing vertical lines. And so the read order is going to be, as we read along the array, that'll be reading down the screen. So imagine like that. But otherwise, nothing too special there. What I want to investigate is just a naive raycasting algorithm. So you've probably seen this a bunch of times. We have a wall and there's some sort of camera looking here, and the approach is basically to divide into grids and say, oh, we go from here to here, and then we step vertically or horizontally, do some math. Okay, we'll step vertically, now we'll step horizontally, and that sort of approximates the line. That's not what I'm doing. That's not what I'm doing. That's all predicated on the fact that floating point calculations were prohibitively expensive, and we are removing that restriction. So instead of that, just imagine a wall which is defined in 2 dimensions as just having 2 points. And there's a camera which is defined as having a point and a direction. So the camera shoots out a ray, and this is like ray casting in the style of ray tracing. But anyway, so the ray will hit at some position, will intersect at some position. And by the way, I hope you're comfortable with vector math, because I'll be using a lot of it in this video. If you're not familiar with vector math, I have made videos on this stuff, and Google exists as well. This is more an entertainment video than anything. Okay, so the position of intersection is on the ray, so it's the ray's origin plus a scalar parameter times the ray's direction. The goal is to calculate the value of that scalar parameter. Now the wall has also the property that it has a normal, and the normal is orthogonal to the direction vector in the plane, in the wall. So from the origin out to the intersection point, if I call this, just call this point A. So if I take the point minus A, that is orthogonal with the normal. In other words, the dot product between those two is 0. So we can just play around with this, sub in the expression for the ray, and then we have, let me just put this here, origin minus A, and then the dot product is a linear operator, so we can split components out. And the parameter t is a scalar, so we can factor it out. So then the goal is to solve for t. You can probably see already what we've got here. We have, so I've just subtracted that inner product, dot product from both sides, which is applying a negative to that, and that's why this order flips around. And so we can now solve this expression for t. Just like that. So then I guess what we can do is just check if this denominator comes out to 0. If the denominator comes out to 0, we know the ray isn't going to hit the wall. And as well as that, we need to check that we've actually hit a point on the wall. So see that this wall is like a constrained line segment. So as an example of a line segment which will hit the wall but not in its range, if we take this ray which is going out here, if we extended this wall, there would be an intersection point. So we need to check for this as well. What we can do is take the direction vector where we would theoretically be hitting the wall and somehow measure how far that is out from the start point, and then divide it by the span, which is the length of b minus a. Okay, so I'll call this parameter u, and this parameter is pretty much, let me just briefly write this. It's the length from the point to the origin of the wall, divide by the length really of the wall. And then we have if, whoops, that's the scalar, not a vector. If u is between 0 and 1, then we're good. Otherwise, yeah, we've missed the wall. We've shot too far to the far or left of, right or left of it. Anyway, so point is, that's the math behind raycasting, pretty much. But then why didn't we do this in the 1990s? Well, basically because computers were incredibly slow at floating point calculations. They almost weren't designed to do it back then. However, modern computers can. So this is what that looks like. All right, pretty good, pretty good. So then the next thing is I'll just write this out again. So we're writing, setting out a whole bunch of elements in an array, and it's 4 floats per pixel, 4 floats per pixel. And we've got some color that we're putting in, which has 4 floats. So we could be setting this color buffer 1 element at a time, and so on. But we could also take advantage of SIMD. So with SIMD, we can set up to 8 floats. So we can take the color that we're inputting, copy that into a SIMD block. So that can fit 8 floats, which in this case is 2 pixels. And then we can actually be setting 2 pixels at a time. Just like that. So, doing the whole thing, but just setting 2 pixels at a time, what does that look like? Okay, fair enough. So we can set pixels. Now, another situation is we should probably have a look at the scene. So the scene, imagine we have a bunch of walls, whatever they look like. And what we're doing is we're sitting somewhere and we're shooting out and we're testing a wall. But we're not just testing one wall, we're actually being naive, we're testing all walls, and that's a problem. So one thing we can do to speed this up is look at subdividing the space. So imagine a box which covers roughly half the scene. Then we split this again. And now we have one box which just covers one line segment. So these ones are fine. And then we'll just continually, keep going and going and going. So for instance, a little messy, but just, keep going. Ugh, I'm bad at drawing, but recursively subdivide the space until we have, in each case, a box which just encloses one line segment. Then when we shoot the ray, we can pretty quickly rule out a lot of these other regions which are obviously not going to be visible. Now, I've talked a bunch about this, and really there was nothing tricky about this implementation that goes beyond the acceleration structures I've done before, but I was just curious to see how it performed. And the answer is, it did not perform well at all. Oh well, it happens. But that did get me thinking. So imagine we have a wall, and we need to, for each pixel on the screen, shoot out, well, not even each pixel on the screen, but you know what I'm saying, each horizontal, each scan line of the screen, shoot out a ray to test against some objects. But remember, we've got SIMD. So what if we shoot bundles of rays instead of a single ray? Let's say, for instance, we can take 4 at a time, and we can sort of shoot those 4 rays all in one go. Now, I have AVX2, so I'm actually shooting 8 rays at a time. That's got to do something. So what does that do, shooting 8 rays at a time? That was encouraging. Now, it is not quite, it's not a very, what am I saying? It's not a dramatic speed up. And it's actually surprising to see that I'm getting about, 1700 frames per second. And if all I do is just do no ray tracing and clear the screen black, that's getting about 2000, 1900 frames per second. So clearly that's not the bottleneck. So we're going to have to go with the nuclear solution. And the nuclear solution is a Vulkan compute shader. Now, they definitely did not have these in the 1990s, but I'm on holidays, so this is a lot of fun. Now, the basic idea is that we have the screen. There we go. That's the screen. And then we dispatch a whole bunch of little jobs. And each job is going to represent a scan line on the screen. So let's say we do this job here. We can do all the ray tracing stuff, work out what we see, and then draw some vertical line of the screen based on that information. And then we go and do the next one and draw a different line of the screen based on the information, and so on and so on. But because this is a compute shader, it is incredibly parallel. As a matter of fact, a compute shader can dispatch 64 work groups at one time. So at any time, you've got 64 threads doing their thing. We've also got a whole bunch of cores, so it's just going super, super fast. So imagine, okay, we have 640 scan lines as we go across from left to right. Divide by 64, there are 10 work groups needed to draw the screen, which is incredibly small, especially compared to ray tracing. So, grand reveal. Vulkan compute shaders, what does that look like? And there we have it. We're currently running at close to 6,000, I'd say. Yeah, between 5,000 to getting up to 6,000 frames per second. That's crazy. That's crazy. We definitely didn't have this in the 1990s. Well, I hope you had fun here. Look, I'm not trying to make a tutorial today. Wasn't pushing out any agenda or anything. I'm on holidays and I was just mucking around and thought this stuff was super cool. But yeah, thanks for sticking through it and have a good one. I'll see you around. Alright. Bye.